In the previous video, we talked about the definition of capacitance, and we talked about the use of the water analogy to understand capacitors. I'm going to do the same thing and take a little bit longer look in charging a capacitor. As we talked about, a capacitor is formed by having two metal plates with the space between them, and that we move charge from one plate to the other, thereby creating charge separation. This is usually done by what's called a battery. And in the battery, there's a positive side of the battery and there's a negative side of the battery. This, which we'll talk more about later, is the symbol usually used for a battery. Although if a power supply is used, they will sometimes use this symbol where they put a plus and a minus with a circle to represent a battery or power supply. Now, a battery does not create charge. It is impossible to create or destroy charge. Charge is never created, never destroyed. It is a quantity that is conserved throughout the universe. But you can move charge around. And so if you take two plates that have no charge on them right now, neutral, then that doesn't mean they don't have charges. It means that they have an equal number of negative and positive charges. Like this. There's some positive, there's a negative. For every positive, there is a negative charge. So the net charge is 0. I can take and move some of these charges. Now, which charge moves depends upon the materials in question. For most solids, especially conductors that we talk about that are metal, the actual moving particle is the electron, and so negative charges move. But in semiconductors, you can have something called holes, which are positive charges that move. And inside chemical things like ions and gases, you could either have positive or negative or both charges moving. When Ben Franklin and others were working on this stuff in the 17th and then later in the 1800s, they didn't know what was actually moving. They didn't even know about atoms or electrons. So they defined the flow of positive charge, we're going to find, as the direction that the charge moved. In other words, whether you move a positive charge or a negative charge, it has the same thing. The positive charge will go in one direction is equivalent of a negative charge flow in the other. We'll get to this in more detail in the next chapter when we talk about current. But the point is that I'm going to say that this battery, and what this battery says, is that into the minus side it will pull negative charges. And it will pump them out the positive side. It does not create charge. It pumps it like a water pump pumps water. So when I close the switch here, close that switch so this becomes connected. This battery, this charge pump, will begin to pull some of these positive charges out into this wire and make them flow into the minus sign, out the positive sign, and up onto this plate. Now what that will do is that will add some extra positive charges. It also means that these charges are no longer here. So that's left behind unbalanced negative charges, exactly the same amount of negative charge as the positive charge on the other plate. This separation of charge is called charging a capacitor. So the amount of charge ends up on this side is positive, an amount equal to Q. And likewise, left on the other side is an amount of minus charge that's no longer balanced. I count 1, 2, 3, 4, 5. So we'll put 5 up there. This separation of charge creates electric field from the positive charges to the negative. The shape of that field depends on the geometry of these plates. For parallel plates, they happen to be straight lines and constant. Now, if there's an electric field, that it means if you put a positive charge here, it experiences a force. Then if you were to push it the other way, you would have to do work against it, and that would store potential energy. So now, because there's a field, there's also a potential difference. If there's nothing else in this circuit, this voltage we're going to find out, this potential difference, will equal the potential difference across the battery. So if this battery is 3 volts and you connected directly these plates, after a short period of time, there will be 3 volts across these plates. If there's 10 volts, there will be 10 volts across these plates. The separation of charge, like I said, is called charging a battery. Now you can also discharge it. If you were to break this circuit, say crack it here, then these positive charges are stuck. They can't get over here. But if you were to connect a circuit between here like a wire at some later time, let's say like this, then these positive charges would be attracted to those minus charges. They would flow along that wire and they would eventually cancel them all out. That is called discharging a capacitor. Now, that means that all the energy that was stored would have to be released. A capacitor can store a large amount of energy. In fact, if the capacitor is comparable to the size of your hand, it can literally vaporize a screwdriver and can certainly kill you, which gets the famous thing that people say in electrical engineering: keep your cotton picking hands off cans. If it looks like a can, like your hand, it can kill you, so don't touch it. Most capacitors and circuits are much smaller than this, and therefore they don't pose a lethal way. But the key thing is, even if you unplug the battery, take it out of the circuit, unplug your television set, if it has a capacitor, it can have stored energy, and that energy, if it's released incorrectly, can actually hurt you. So you have to really understand what you're doing with these electronic piggy banks. This is why they tell you not to play in the back with your television set. All right. Let's do an example problem. A battery transfers 2 microcoulombs of charge between the plates. So it takes 2 microcoulombs of positive charge from one plate to the other, leaving a minus 2 microcoulomb charge on the other plate. So I've got one plate, I got plus 2 microcoulombs on this plate. And on the other plate, I have minus 2 microcoulombs. So Q, when we do this, the total Q is always 0. When we're talking about the Q, we mean the charge on one plate, the positive plate. 2 microcoulombs. The voltage difference, it says, from here to here is 4 volts. And it asks you, what is the capacitance? This is just an application of the definition. Q is CV. C is Q over V. This is always the way you find the capacitance. All other formulas that we may get to later are derived from this formula. So C is 2 microcoulombs over 4 volts. And this is 0.5 micro. A coulomb per volt is a farad. Notice how I did not convert into exponential notation. Get used to playing with the SI units. They make the calculations faster. This is a pretty good sized capacitor. Most capacitors are on the order of nanofarads or picofarads. A microfarad capacitor has a little bit of whop. A millifarad or a farad capacitor are lethal, potentially, if they have enough voltage across them. Okay, talk to you on another video.